Hey folks, welcome to Unit 7 on oscillations. This unit's going to be very brief. We're going to start off by defining simple harmonic motion and explaining it in terms of period and frequency, and then we'll transition to energy and motion graphs. So we'll start by just defining simple harmonic motion as a wordy definition that we're going to dissect, and then we'll look at an example of simple harmonic motion with a spring. Simple harmonic motion, which you'll see abbreviated SHM, is a periodic oscillation that results from a linear restoring force. So lots of vocab in that sentence. We know a lot of that already, but we'll see. Periodic just means that it's something that repeats regularly. And so we've covered that already with circular motion. Oscillation is any back and forth motion around a central point. So, flicking a light switch is technically an oscillation, but simple harmonic motion is a specific type of oscillation. So any back and forth motion is an oscillation, but only some oscillations are simple harmonic motion. This linear restoring force is the most complicated one. By restoring force, we mean that it's a push or a pull toward the central point. That's the restoring force part. The part that makes it linear is that it's a push and pull toward the central point that is proportional to the object's displacement from the central point. So what that means, and then we'll go back to the definition, is that the further away an object gets from the middle of its oscillation, the greater the restoring force is. It's a linear relationship. So, a graph of force versus displacement would give you a linear function. So to put all that together, we can say that we have a back and forth motion that repeats regularly, that is also governed by a push or a pull that always points toward the central point and is proportional to how far from that central point the object is. So take some time to digest that definition, maybe pause the video or come back to it after the video, but make sure you do consider all of that. I'm using this phrase central point in the definitions, and central point of an object in simple harmonic motion is going to represent the equilibrium point. And we know about equilibrium, that's when the net force equals 0. So it's not that the object isn't moving, it's just when the object passes through that central point of its oscillation, the net force is 0. And that's how we know it's the central point. It's when the net force is 0, and vice versa. So we're going to look at one example. That's a mass spring oscillator. We really only focus on two types of oscillators, a mass and a spring, and then a pendulum. And so the derivation or the mechanics of a spring is easier to cover in a short time. So I'm going to focus on that one. And then for this curriculum in this course, you'll just have to kind of trust me that a pendulum works the same way. There are plenty of videos out there that derive this relationship for a pendulum. So because we have a mass on a spring, the typical orientations are horizontal and vertical. If it's a horizontal spring and mass oscillator, the mass goes back and forth, left and right, along a frictionless surface. We can say all the same things if that spring is hanging from a ceiling or a hook, but it's easiest to talk about the horizontal ones first. Now we have an equation for Hooke's law, that the force exerted by a spring is equal and opposite to the product of the force constant and the displacement. So that spring force always points in the opposite direction that the spring has been compressed or stretched, and it's proportional to distance. This is what we mean by a linear restoring force. So if this mass is pushed to the left, the spring is now pushing to the right with some force. And that is because the displacement is in the opposite direction. So the displacement is to the left and the force is to the right. And that's the negative sign in Hooke's law. That's the significance of that. Okay, so we have the force that is proportional to displacement, and we know that the net force is equal to mass times acceleration. So what we get when we put that together is mass times acceleration is equal to negative k delta x. So force and displacement are always opposite in direction. And then if the displacement is 0, then the net force is 0. The acceleration and the net force are both 0, and we call that equilibrium. And then this relationship is linear. So the force being proportional to displacement, but opposite in direction. If I graphed the force exerted by the spring versus the displacement of the mass, because they are opposite in direction, I would get a line that looked like this, which initially is like kind of hard to digest. If we were to push the mass to the left, that's the negative direction for displacement, we would get a positive force, a force that's in the opposite direction. And then if we were to pull the mass to the right and stretch the spring, we would get a negative force in return that's pushing back toward that equilibrium point. And then, different springs have different force constants, and also you can put a different mass on that oscillator. So the values of K and M determine the slope of that line. So, we covered Hooke's law a bit in the forces unit and the energy unit, and so we're not going to do much more with that. But that's your intro to simple harmonic motion. This force varies with position in a linear fashion, and so it's something that can create that oscillation, that's simple harmonic motion. And so we'll talk about this and a pendulum in the next video.